Welcome everyone to something slightly different from River Publishers. Today I have with me a number of different people. So first I have Nicki Dennis from River Publishers and Andrea Vacca, the editor-in-chief of our international journal of Fluid Power. And today we are announcing and discussing the best paper from 2022, which was awarded to the paper A Piezo-Electric Valve Actuator for Hydraulic Exoskeleton Drives. We have the two authors with us, Philip Albrecht-Zagar and Rudolf Scheidl, to chat about the paper. Welcome everyone, especially to Philip and Rudolf. Thank you so much for joining me. Just to start with, Nicki, would you like to introduce the journal a little bit and what it covers?
Hi, yes, thanks, Philippa. Yes, so the International Journal of Fluid Power was established in the new millennium at 2000, and it's the first scientific journal fully dedicated to fluid power technology in the English language. It's aimed to provide important information to engineers and academics who are interested in advances in modern fluid power technology. We are very lucky to have Andrea Vacca from Purdue as our editor-in-chief, and we have close links with the International Society for Fluid Power. River Publishers acquired the journal in, I think, 2019. And since then, and also since Andrea's involvement, I think more from him than for us, we've seen a steady increase in both the impact factors and the quality of papers. And that is reflected in us now being confident about awarding best papers. So that's it from me.
Great, thank you. Andrea, did you want to add any thoughts on the journal or why you kind of chose this best paper for 22?
Yeah, no, I think that Nicki introduced the journal greatly. And yeah, the journal is very active also in participating to conferences that the Global Fluid Power Society sponsors. And that gives really many submissions that are right on the topic of fluid power. We didn't mention what is fluid power in general. Is the discipline that uses pressurized fluids to perform mechanical actuation. So it's very vast discipline that there are machines using fluid power systems in all possible engineering applications. And then we also do research in isolated problems that are fundamentals for either the system or the component. So yeah, we, as you said, we are linked to the Global Fluid Power Society, and so it's not easy to get a paper published into the journal because reviewers are usually very qualified into that. So we have an acceptance rate that is fluctuating from 40% somewhere there. So we are quite selective, and yes, we every year we. Lately, we decided to award a paper, and usually the metric that we take into consideration the most is the number of views. That gives more what is the true impact that paper has to the audience. So for the past year, the paper that was published by Philipp and Rudolf got way higher views than other papers, so that was a nice, really nice news and to see. And of course, we also consider what were the comments from the reviewers when the paper was taken in. So we want to ensure that we pick a paper of a good quality for our awards, of the best quality. So that is what's behind. So now back to you.
Great, thank you. And now moving on to talk a bit more about the winning paper. Firstly, Philip and Rudolf, congratulations on having your paper chosen. To begin with, could you please introduce yourselves a little bit and the paper a bit more? Perhaps Philip, you'd like to start.
Philip? Or okay, yeah.
Yeah.
Okay, so thank you. I'm really honored to be chosen. So my name is Philip Albrecht-Zagar, and I am working at the Institute of Machine Elements and Hydraulic Drives at the Johannes Kepler University with Professor Scheidl. This for 4 years and a little bit more, like 4.5 years. And I am a PhD student there. And yes, I studied, I first attended the technical school in chemical engineering, and afterwards I studied electrical engineering, so I'm actually from a different field, at the Technical University in Vienna. I did my bachelor's received my bachelor's degree in 2012 and received my master's degree in 2014. And then I went into industry for 4 years. And I worked with E+E Electronics, which is a developing company for gas sensors. Yes, so my research is focused mainly on 2 things. The first thing is the modeling aspects and reduction of dynamical systems, of especially hydraulic systems, and the second aspect is investigation of piezoelectric valve actuation. So this last part of my research is also this paper about. And so so maybe to Professor Scheidl, I think he also wants to say something.
Okay, yeah. I have been working in fluid power for more than 30 years at the university. Since October of last year, I'm retired, but I'm still in connection to the institute, in particular to the PhD students, which are still on their way to finishing their work. And it's also true, of course, for Philipp Albrecht-Zagar. Maybe a bit of the motivation why we went to piezoelectric actuation. We started working on fast valves, so in the beginning of 2000s for some industrial applications. At that time, we were thinking of using either piezoelectric actuation or solenoids, and at that time we decided for solenoids for some reasons. It was not so easy to get piezoelectric actuators. It seemed that more appropriate to get to a fast result taking solenoids in that time. And for a very long time I believed that for practical reasons solenoids are more attractive and more competitive. But this a few changed when I had the opportunity to kind of co-supervise a PhD thesis from Dresden University of Technology, supervised by Jürgen Weber, which was about a kind of dosing pump for medical applications. And the PhD student, he was very good thesis. He brought forward very good arguments why, especially for this application, piezoelectric actuators have some convincing advantages. That made me changing some mind, and at the end of my active times at the university, to rethink of my former positions and ask a young researcher like Philippa Albrecht-Zagar to consider it. I mean, the main advantages are I expect them to be a bit more compact, be a bit more efficient. And for some applications, particularly those that we had in mind for his thesis, namely the usage for exoskeletons, so applications in the environment of the human body, it seemed to be at least worth making some research on it. That is my position. Thank you.
Okay, and I think now I give a short introduction to the paper, what it is about. So the paper is basically about a piezoelectric actuator, which should actuate a spool of a switching valve. And of course, a piezo has some kind of downsides, especially the small displacement. And to overcome this, we introduced a buckling beam to get some amplification effect on this low displacement. So what we basically did, maybe I can share the screen.
Yeah.
So can you see this slide?
Yeah.
Okay, so what we basically did is we constructed so we have here a piezoelectric stack, and which is attached to some frame, which I call the U-form, because it's formed in a U-form. And then this piezo stack is expanding, and this lever arm amplifies the displacement already. But the second amplification mechanism is the buckling beam, which is attached here. So it is a beam which is pinned at this and this end, and then buckles to either the left or the right hand side. So this buckling beam can then be attached to a spool of a valve, and then you can switch some hydraulics by using such a concept. And so this paper is mainly about the design of such an actuator. And all the thoughts that we came up with, and all the problems that we saw. So here is a video of the prototype of the actuator, which is switching just once.
Mm-hmm.
And you can also switch it quite fast. So here is the switching. Here's the displacement and the time in milliseconds, and you can see here it switched. Yeah.
Wow.
So this is the concept of the prototype of the actuator, and the paper basically deals with the.
That's great.
Great, thank you. Andrea, I know you had a couple of questions. Do you want to kick off with those?
Yeah, no, this is really great stuff from my side, and I'm curious about the target exoskeleton, and that makes me think that this has actually a very wide application when I see that. So can you elaborate why you target there, and maybe you can comment how this can go to components that are perhaps more at the size that we are used to see in large machines, if that is a technology that can go on those applications. So I don't know, Rudolf or Philipp, if you want to ask on that. Yeah.
Maybe I answer. I mean, it is not limited to exoskeleton use. That was just you need an application scenario, certain size in order to run prototyping. It's not limited, of course. If you think of very large valves, you can, of course, use hydraulic amplification. That's a way that is often done also for solenoid valves. So that is an option. At the end of the day, so to say, if you can give some foresight about the practical applicability, it depends on various circumstances. The first is, of course, cost is always an issue in engineering. The second thing is, we need relatively high voltages, even though nowadays we have 100 volts that is feasible. We need some reasonable power electronic devices that can supply a very fast current or very high current in short time. In order to do this efficiently, you need some special circuitry, which Albrecht-Zagar, Philip Albrecht-Zagar can explain in much better way since due to his electrical background and cabling and so on. So this is there are a lot of practical things that are related to this question, but it is open. At the end, it is the complete package, cost, robustness, which decide on the applicability. And yeah, that's it. And these data, of course, have to be given by industry. So at university, we can do some good research, but it's very difficult for us to give production costs and such things. That's an industrial thing.
So you think it's scalable to other application, even for high flow rate?
I mean, not for a direct actuation. I like also for solenoids. If you have, let's say, valve of nominal size 16 or so or 20, then you also hardly take direct electric actuation. You also use some piloting stages, and this is feasible here as well. The question is, when does it pay? I see two advantages. I repeat a bit what I brought forward. The first is maybe it's a bit more efficient. They are faster, which is not always needed. And they are a bit, maybe they are, have lower weight, which is not always an issue, but it is one. When you look at the solenoid actuated valve, I mean, it's often 60, 70, or 80% of the weight is taken from the solenoids. So if we, for some applications, exoskeleton, of course, also, if you use many valves, this can be an advantage.
Oh, I see. That's very interesting. Yeah, I didn't thought about that. And Philip, you mentioned on a little bit on how fast you can be in the actuation. So can you comment on what is the commutation speed that you were able to reach, and how would that compare to a solenoid valve technology? Yeah.
So that what you see in the video, that was basically just the buckling beam that was switched. So of course you have a mass additionally at the center point, which is the spool mass, and this is basically determining how fast you can go, because this is this basically defines the characteristic eigenfrequency. Of course, this application is, or this actuator targets applications for very small hydraulic valves. So, like, let's say 2 liters per minute or something, and so such valve or spools you can make quite small, and so the masses are not that high. So I guess the actuation speed can be like less than 5 milliseconds or something, or like in the range of some milliseconds, let's say.
Yeah. And so that's very interesting. So I don't know, Philippa, if you have other questions, perhaps.
Nicki, did you want to say something?
Well, I mean, I'm not a fluid power engineer, but I can see that anything that brings together electronics, mechanical engineering, and some sort of basic electromagnetism physics to help things happen at a novel way, in a faster, cheaper, more reliable way than has happened before is it's groundbreaking. It's fantastic. And now, as Rudolf says, now it's the universities to create this. Is now for industry to look at this and see how they can implement it and get the advantages from it. Will be fabulous. Yeah, it's great.
Okay, great. Philip, you mentioned earlier the paper also included some of the problems you kind of came across when developing this. I was just wondering what some of the challenges are for developing an actuator like this that uses like the buckling beam.
Yeah, so there is, of course, those challenges that come with piezoelectricity. Which is mainly the small displacement, and then also the difference in thermal coefficients, expansion coefficients in piezo ceramics and steel, which is quite different. Also hysteresis and creep and stuff like this, but we didn't tackle the piezoelectric problems that come apart, but only the displacement problem. And on the other side, when you use a buckling beam, there is mainly the problem of friction in the pinning points, in the pinpoints. So if you want to swing the buckling beam from one position to the other, then of course you have friction also in the pinning points, but also if you attach it to a spool in the casing or in the spool, in the hydraulic valve, and this deteriorates the swing phase. So you might not reach the other position if the friction is too high. And I tried out, but this was not very successful. I just mentioned it shortly in the paper. I tried out to use jewel bearings for this problem. We then didn't go further on with this, but there with the first test you could see that the friction is getting lower by applying such fancy bearings. Yeah. Yes.
Okay, great. Is that the focus for kind of your future work in this area, looking at that friction?
No. What I tried to do in my future work, or actually it's my actual work right now because it was published a few years ago. I then came up with some other ideas to get the piezo stack even smaller, which works like this. You don't need the piezo to expand so that the beam can swing through, but you need the piezo only to kind of weaken the buckling beam, and then the buckling beam can snap through. So by doing this, you arrive at a design where the piezo stack can be very much decreased, so the length of the stack, and so you also get rid of the problems of high inrush currents, for example, because you don't have that high capacity anymore, and also you can miniaturize it further on.
Okay.
And this concept was already published last year, where we also tried to fed back the output of the valve and thereby use the hydraulic energy that is in that we want to switch kind of to help the buckling beam to snap through. So by these tricks, you kind of you can come up with designs that are even smaller and are not that prone to errors as it would be if you just rely on the swing phase, on the proper swing phase.
Maybe if I add, in this case, the piezoelectric actuator is actually a latch and not an actuator for the spool valve. So the motion is actually driven by a hydraulic force that is fed back is to make actually the valve unstable. And the piezoelectric system with a snap-through spring that is just a kind of a brake or a latching element. These are ideas that come of also of electronics. Electronic engineers play around with such effects since long time very successfully. In hydraulics is a bit more. Is not so clean in its effect side. That's why it makes it much more difficult to realize such effects in hydraulics. In this case, it seems to work, but not always, unfortunately.
So back to the beginning, you said that the motivation for you, Rudolf, was, to go back and explore the use of this technology as compared to solenoid. That instead you base your work for many years on. So now you change idea.
That's it. That is one of my learnings as an old man, so to say. Sometimes you focus and you give preference to a certain technology for good reasons, for good arguments. You seem it more appropriate for a certain range of applications. One always should stay open and open for new technologies. Of course, you cannot run all technologies in parallel in your research work. That is too much of workload. So you focus on something, and maybe you should be ready to learn your lessons and switch to another ones in other phases. That's it. And I never would say after my 3 decades of experience in fluid power, I never would say this is one technology. When I was starting, I was thinking about making everything less or more in a mechatronic way. Even this I don't see any longer. For some applications, conventional ways doing things hydromechanically are advantages. In other cases, the massive use of electronics is better. It depends very much. And as a researcher, we have an relatively easy play because we just can investigate, we can explore. We do not have the load to convince customers to a certain extent, yes, but let's say our survival, our business survival does not depend so much on the right choice of the proper technology. That's why it's a bit easier. And also, I think our duty to explore these things.
Yeah. So we look forward to a follow-up paper. Yeah.
Great. Well, that's actually quite a nice place to end it. We're kind of running out of time, but Andrea, would you like to have any last words on why you chose this paper and why it was the best paper from 2022?
Yeah, no, and I think I mentioned already at the beginning, but I want to reinstate that every year we kind of go to the very top papers that we have. So we kind of try to get best 3 or best 4, and then it's not just a decision of the associate of the editor-in-chief, myself, but I involve also the directors for the Global Fluid Power Society to if there is a consent to on one paper. And so if, for this case, there was no discussion. This was very interesting work on a very new technology, including theory, including experiments. So it makes really what I would say a research paper complete. So my congratulations again to the authors. Yeah.
Yes, congratulations, Philip. Congratulations, Rudolf. Thank you so much for joining me and everyone else today.
Thank you.
Thank you. Bye.